Hello everyone, welcome back to my channel. So today we will learn about metric spaces. First of all, we will start with the definition of metric space and we will look at some standard examples of metric spaces. So first of all, let me start with the definition of a metric space. Okay, so let X be a non-empty set. Okay, a function, a function D from X cross X to real numbers is said to be a metric is said to be a metric on X if it satisfies the following conditions. Okay, so what are the first condition? The first condition is like this. So d of x comma y should be greater equal 0 for all x comma y belongs to x, and d of x comma y equal to 0 if and only if x equals to y. The second condition is this: d of x comma y should be equal to d of y comma x, and this should happen for all xy belongs to x. Thirdly, d should satisfy triangle inequality, that is d of x z should be less equal d of x comma y plus d of y comma z for all x y z belongs to x. In case suppose D satisfies all these conditions, then we call D as a metric on X, and then X becomes a metric space. Okay, so the ordered pair X, which is an empty set taken by us, and D is a function which is proven to be metric, is called as a metric space. Is called as metric space. Now let's go and watch some examples on metric spaces. So we will start with first of all real numbers, and we'll try to define a usual metric, okay, or we may also call it as a distance metric, okay, on real numbers. So the very first example, so let me take x equal to real numbers, okay, and define d from real numbers cross real numbers to real numbers as d of x comma y is equal to mod of x minus y. Okay, we'll prove that this particular d is a metric, okay, and R forms a metric space under this metric, and this metric is called as a usual metric. Okay, so let's show this one by one. So for the first property, we know that firstly we know that mod is always non-negative, right? So mod of a is greater equal 0 for all a belongs to real numbers, right? So definitely this implies mod of x minus y will also be greater equal 0. So that clearly implies that d of x comma y is greater equal 0. Okay, further I want to show that d of xy equals to 0 if and only if x equal to y. So further d of xy equals to 0 if and only by definition mod of x minus y equals to 0, but mod of number is 0 if and only if that number is 0. So that is if and only if x minus y equal to 0, and that is if and only if x equal to y. So automatically first condition have been established. Okay, so let's now try to prove the second condition. Second condition is also equally easy. So what is d of x comma y? So d of x comma y is actually equal to mod of x minus y, but we know that mod of x minus y is same as mod of y minus x. So now as x and y have changed their positions, now this is d of y comma x. So d of x comma y becomes equal to d of y comma x. So that is the second condition which have been established now. For the third condition, we will go like this. What is d of x comma y? So that is actually equal to mod of x minus y. So I will insert one point z. So I will write it like x minus z plus z minus y. You know that mod of a plus b is always less equal mod of a plus mod of b. So this is less equal mod of x minus z plus mod of z minus y, and by definition this is nothing but d of x comma z plus d of z comma y. So automatically we have established third condition as well. So D satisfies all the three conditions of metric. Okay, so that's why D is a metric on R, and we call this metric as a usual metric. Okay, so R forms a metric space under this usual metric. Okay, now we will move to the next example so that we can have a clear idea of so many metric spaces. So let me take next example. So for the second example, I will take x equal to R2. Okay, and define d1. Let's change symbol so that we can identify this metric later. So d1 from R2 cross R2 to R as d of x comma y is equal to mod of x1 minus y1 plus mod of x2 minus y2, where since we are taking x and y both from R2, then must be ordered pairs. So here x is x1 comma x2 and y is y1 comma y2, right? So let's now try to identify that this particular d1 is also a metric on R2. So for a solution, first of all, we'll try to establish conditions one by one. Since you can observe here that this is your mod, this is mod of x1 minus y1, so this is non-negative. This is mod of x2 minus y2, so this is again non-negative. So sum of two non-negative numbers is again non-negative. So this particular d1 of x comma y is always non-negative. Okay, so that condition can be easily established. Okay, so since mod of x1 minus y1 is greater equal 0, comma mod of x2 minus y2 greater equal 0, so this implies their addition, that is mod of x1 minus y1 plus mod of x2 minus y2 is also greater equal 0, and as per the definition this is nothing but d of x comma y. So d of x comma y is greater equal 0. Now further, let's find a condition where d of xy becomes 0. So d of xy equals to 0 if and only if, by definition, mod of x1 minus y1 plus mod of x2 minus y2 equal to 0. We can easily identify here that both of these numbers are non-negative, right? So the addition is 0 only when both of them are 0. So this is possible if and only if mod of x1 minus y1 equals to 0 and mod of x2 minus y2 equals to 0. That is if and only if x1 minus y1 is 0, and here it is possible if and only if x2 minus y2 is 0. Okay, so further we can simply establish that this is possible if and only if x1 equals to y1 and x2 equals to y2. So that is if and only if ordered pair x1 comma x2 is equal to ordered pair y1 comma y2, and that is nothing but if and only if x equal to y. So d of xy equal to 0 if and only if x equal to y. Now let's try to establish the second condition of metric. So for that, I will start with d of x comma y. As per the given definition, this is mod of x1 minus y1 plus mod of x2 minus y2. But we know that mod of x1 minus y1 is same as mod of y1 minus x1 plus this is mod of y2 minus x2. Now one can observe that y1 y2 are in the first position, x1 x2 are in the second position. So as per the definition of metric, this is simply d of y comma x, right? So second property can be proved in this manner very easily. Now let's try to establish the third and final property of metric. For that, let me start with d of x comma y. So that is equal to mod of x1 minus y1 plus mod of x2 minus y2. Now I will try to insert one new point z, that is z1 z2 in this. So we can insert it like this. This is mod of x1 minus z1 plus z1 minus y1, and coordinate z2 will be inserted in the second mod, that is mod of x2 minus z2 plus z2 minus y2. So this is simply, now we can write that this is less equal as per the definition of mod which we have already discussed. This is less equal mod of x1 minus z1 plus mod of z1 minus y1 plus this is also less equal mod of x2 minus z2 plus mod of z2 minus y2. Now what we'll do, we will just rearrange terms as per our requirement because we need d of x comma z. So coordinates of x and z should have the first positions and then coordinate of z and y. So I will just shuffle these terms. Okay, so this is just mod of x1 minus z1 plus mod of x2 minus z2. And secondly, this is mod of z1 minus y1 plus mod of z2 minus y2. So simply we can find it here that x1 x2 are in the first position, z1 z2 are in the second position. So as per the definition, this is d of x comma z plus z1 z2 are in the first position, y1 y2 are in the second position. So this is d of z comma y. So we have established that d of x comma y is less equal d of x comma z plus d of z comma y. So this particular d1 is also a metric. Okay, we need to do only one change throughout the solution, that as we have taken d1, okay, so we have to replace d by d1 everywhere inside the solution. So let me do that. Okay, so that clearly means that d1 is a metric, okay, on R2. This metric d1 is called as some metric on R2. So d1 is metric on R2. It is called as some metric on R2. If we'll move to the next example, we can easily establish one more example, that as we saw in the first example that it was usual distance on real numbers, we can take distance between two ordered pairs in R2. So we will write that example here now. So I will move to the third example. So this is very important metric actually. So I will write D2 from R2 cross R2 to R, and we will define it as d2 of x comma y is equal to square root of x1 minus y1 square plus x2 minus y2 square. You can easily tell that this is nothing but distance between points x and y, where point x is x1 comma x2 and point y is y1 comma y2, right? Okay, now let's try to verify that d2 is a metric. Okay, so the very first situation we can easily find that since we are dealing with squares, so mod x1 minus y1 square is non-negative, whatever x1 y1, but x1 minus y1 square will be non-negative, x2 minus y2 square will also be non-negative, so that addition is non-negative. Okay, and square root of non-negative number is non-negative whenever it exists. Okay, so that's why we can easily find that d2 of x comma y is a non-negative number. Okay, So let's try to establish the remaining facts. So I will go with the next remaining facts. Now let's try to understand when d2 of x comma y is 0. So this is 0 if and only if that square root is 0. So that is if and only if square root of x1 minus y1 square plus x2 minus y2 square equals to 0. That is possible if and only if the number inside square root is 0. So that is if and only if x1 minus y1 square plus x2 minus y2 square equals to 0. That is possible if and only both the numbers are 0, because both the numbers are non-negative. So addition of non-negative numbers is 0 if and only if each of them is 0. So this is x1 minus y1 square equals to 0, right? And x2 minus y2 square is also equals to 0. So that is possible if and only if numbers are 0. So x1 minus y1 is 0 and x2 minus y2 is 0. So that is possible if and only if x1 equals to y1 and x2 equals to y2. So we can easily observe here that this is possible if and only if ordered pair x1 x2 is same as ordered pair y1 y2, and that is nothing but if and only if x equal to y. So d2 of x comma y equal to 0 if and only if x equal to y. Now let's try to verify the remaining two conditions of matrix. So now what is d2 of x comma y? So d2 of x comma y is square root of x1 minus y1 square plus x2 minus y2 square. One can easily observe that x1 minus y1 square is same as y1 minus x1 square, and x2 minus y2 square is same as y2 minus x2 square. That is, if we take minus common, that minus 1 square is 1 and sign will be changed. So this is quite simple to understand. So now we can observe that position of y is in the first place and x is in the second place. So this is definitely d2 of y comma x. So that established our second condition. Now let's try to establish the third and final condition of d2 metric. So for that, what we will do, we will take d2 of x comma y. So as per the definition, this is third condition which we are establishing now. So that is nothing but square root of x1 minus y1 square plus x2 minus y2 square. So now what I can do, I can just insert a new point z1 z2, that is z, in this particular square root like this. So z1 will be inserted in the first position, so x1 minus z1 plus z1 minus y1 square plus x2 minus z2 plus z2 minus y2 square. Okay, now we will use Minkowski inequality here. So as per Minkowski inequality, what we can write? We can write that in general, Minkowski inequality reads like this. That means if we have a plus b square plus c plus d square raised to half. Okay, so that is less equal a square plus c square raised to half plus b square plus d square raised to half. Okay, so we'll use this here now. So this will be a, okay, this will be b, this will be c, and this will be d. So using Minkowski inequality, what we can write, this is less equal square root of x1 minus z1 square plus x2 minus z2 square plus square root of z1 minus y1 square plus z2 minus y2 square. So that is nothing but equal to d of x comma z plus d of d2 of z comma y. So we have established that d2 of x comma y is less equal to d2 of x comma z plus d2 of z comma y. So d2 also satisfies all the conditions of metric. So d2 is also a metric on R2, but since it counts distance between x and y, we call this as Euclidean distance, and that's why this metric is called as Euclidean metric on R2. So d2 is called as Euclidean metric. Euclidean metric on R2. Okay, now we will move further and we will see one more example of metric space. So let's deal with the fourth example. I will again take R2, but right now I will define a new metric, that is d infinity from R2 cross R2 to R as d infinity of x comma y equals to maximum of mod of x1 minus y1 comma mod of x2 minus y2. So in short, we are finding supremum of x1 minus y1 and x2 minus y2. Okay, where x is x1 x2 and y is y1 y2, right? So this is metric is called a supremum metric or a sup metric on R2. But first of all, let's try to verify that it is a metric. Now let me just establish some conditions quickly. Mod is always non-negative. So mod of x1 minus y1 is non-negative number. Mod of x2 minus y2 is also non-negative number. So maximum of two non-negative numbers is gonna be non-negative number. So clearly d infinity of x comma y going to be greater equal 0. That's quite easy to establish, right? Now let's try to understand when d infinity of xy is 0. So d infinity of xy is 0 if and only if, by definition, maximum of mod of x1 minus y1 comma mod of x2 minus y2 equals to 0. Now this maximum will be 0 if and only both the numbers are 0, because either one of number becomes non-zero, then that will be the maximum. Okay, so if you want maximum to be 0, then both of these numbers should be 0, then only maximum will be 0. Okay, and after this all the things are quite simple now. So this is possible if and only if mod of x1 minus y1 is 0, and this is possible only when x2 minus y2 is 0. So that gives me access to write x1 is y1 and x2 is y2. So that is possible if and only if x1 x2 is same as y1 y2. Okay, and that is if and only if x equals to y. So d infinity of xy is 0 if and only if x equals to y. So we have established the non-negative of d infinity. Now let's try to verify the remaining two conditions of d infinity. Now d infinity, second condition, d infinity of x comma y is equal to maximum of, you know the definition, that is mod of x1 minus y1 comma mod of x2 minus y2, right? So that is actually equal to maximum of, because mod of x1 minus y1 is same as mod of y1 minus x1, mod of x2 minus y2 is same as mod of y2 minus x2. So this is quite simple to understand, right? This is now nothing but d infinity of y comma x. So that establishes the second property of metric. Now let's try to identify the third property. So to establish third property, first of all, what is d infinity of x comma y? So d infinity of x comma y is maximum of mod of x1 minus y1 and mod of x2 minus y2, right? Okay, again write down what is d infinity of x comma z. So d infinity of x comma z is going to be maximum of mod of x1 minus z1 comma mod of x2 minus z2, right? So actually d infinity of xz is maximum of these two numbers, right? So both of these numbers are less equal d infinity of x comma z. So what this implies, let me just write that. So this implies mod of x1 minus z1 is less equal d infinity of x comma z, and mod of x2 minus z is also less equal d infinity of x comma z. Now further, what is d infinity of z comma y? So d infinity of z comma y is actually equal to maximum of mod of z1 minus y1 comma mod of z2 minus y2. So since this is maximum of these two numbers, again as I've written previously, I can write here this implies mod of z1 minus y1 is less equal d infinity of z comma y, and mod of z2 minus y2 is also less equal d infinity of z comma y. Okay, so now what is x1 minus mod of x1 minus y1? So now mod of x1 minus y1 is actually equal to mod of x1 minus z1 plus z1 minus y1, but that is less equal mod of x1 minus z1 plus mod of z1 minus y1. Okay, and we know that mod of x1 minus z1 is less equal d infinity of x comma z, and mod of z1 minus y1 is less equal d infinity of z comma y. Similar augment can be applied to mod of x2 minus y2. Actually mod of x2 minus y2 is mod of x2 minus z2 plus z2 minus y2. So that is less equal mod of x2 minus z2 plus mod of z2 minus y2. So that is mod of x2 minus z2 is less equal d infinity of x comma z plus this is less equal d infinity of z comma y. Now what can we observe, that this number and this number, both of these numbers are less equal this common number, that d infinity of x comma z plus d infinity of z comma y. So both of these numbers are less equal this common number, right? So obviously their maximum is gonna less equal this common number, right? So what this implies now? So this implies maximum of mod of x1 minus y1 comma mod of x2 minus y2 is gonna less equal d infinity of x comma z plus d infinity of z comma y. But maximum of mod of x1 minus y1 and mod of x2 minus y2 is nothing but d infinity of x comma y, and that is less equal d infinity of x comma z plus d infinity of z comma y. So this clearly establishes the fact that d infinity is also a metric on R2. So therefore d infinity is metric on R2, and this is called as a sup metric, supremum metric. Okay, fine. In the same manner, we can define numerous metrics on given non-empty set X. Okay, but for now, in this lecture, we will restrict ourselves to only D usual metric, D1 that is sum metric, D2 that is Euclidean metric, and D infinity that is sup metric. This metric was defined on R, and all of these remaining metrics were defined on R2. Okay, so further, we will talk about discrete metric. We will also learn about more detailed concepts of metric space. Okay, so stay tuned. Thank you.